Good morning, everyone, and welcome to HRC Trading Academy. As usual, can you please put all your questions into the chat and we'll address those afterwards. In the meantime, I introduce Danny Walensky, our HRC's Managing Director, who will do introductions. Over to you, Dan.
Thank you. A very warm welcome to everybody. Thank you so much for attending. I can't believe the overwhelming support that we're getting. When we opened this webinar, in the first 2 hours, we were already fully booked. So we had over 1,000 people respond. So Duncan very kindly said that he would do another date for us, which is next week. So thanks so much for that. And that one's also nearly full. So just a reminder that you will get 2 hours, CPD hours for this. But if you attend both of them, which is going to just be a repetition, you won't get 4 hours. It's still only 2 hours, okay? But our presenter, Duncan Boyce, has chosen the Honey Badger Boot Camp as his charity of choice. So if you've got a few 50 rands or whatever that you'd like to contribute, it would really be appreciated. Let me just tell you a little bit about this charity. In South Africa, many teenagers face daunting odds raised in single-parent families or foster care. They grapple with exposures to gang life and drugs. Their dreams are stifled and their prospects seem bleak. Honey Badger camps aim to set them on a new path and away from temptation with their communities. Through participation in the Honey Badger camps, teenagers learn about themselves, their limits, new skills, enabling them to be more responsible for their own lives and make better decisions. So it's really a great charity. And if you do have some money, please can you just contribute? All the details will be in the chat. But I'd also personally like to thank Marius Atterbury of the Fire Protection Association. He set this up with Duncan. And let me tell you about Duncan Boyce. He's the chairman of the CETA group. He started off as a teacher, majoring in physics. He later went on to gain tertiary education in marketing management, followed by a financial management diploma and a certificate in fire engineering. However, his passion for business led him away from teaching to undertake several business ventures before ending up in the fire industry. Duncan has spent the past 37 years in the portable fire extinguisher industry, primarily on the manufacturing side. During this time, he has been the chairman of the Centre Group for the past 33 years, chaired the SACWA Fire and chaired SABS Standards and Technical Working Group committees, including representing the SABS at international standards organization meetings. Duncan recently shared with us that he attended the Fire Safety Expo in Birmingham, UK, where he was exposed to new findings pertaining to lithium battery fires, which he has included in his presentation. In short, Duncan has an immense passion for fire and the South African fire industry. So please welcome Duncan and thank you so much. Over to you.
Dilly, thanks very, very much for that very kind introduction. Yes, I am very passionate about fire, but I have to say that this presentation today is not a sales pitch at all. It's just a presentation of the facts of lithium batteries and the fires that can be associated with them. But I also thought I would just take this opportunity, and I'd be prudent most probably not to, just to explain a little bit about the Centre Group. The company was established 33 years ago. It was established as a franchise organization, and today there are over 30 franchisees in South Africa, Sub-Saharan Africa, and the Indian Ocean Islands. We have a very simple byline within the Centre Group, and that's complete fire protection. And that complete fire protection gets covered by 5 divisions. The first division is portable fire extinguishers. The Centre is the only manufacturer of fire extinguishers in Sub-Saharan Africa. The second division is electronic fire detection and gaseous suppression systems. They speak for themselves. Linked in with that are kitchen systems. Then the third division that we have handles automatic fire sprinklers. And there we are the distributors of Reliable automatic fire sprinklers. Reliable, a company that's about 104 years old. Our fourth division handles exports. And our fifth division is our national maintenance and contracts division, mainly maintenance of detection and fire equipment. And in this division, we have developed an app, and the app is linked with a barcode, and this gives our clients throughout South Africa 24/7 viewing of their equipment and the status of their equipment. So I think with that said, and getting my little pitch in very quickly, we need to go back to the presentation. I will share now my screen with you. This is the technological part where I need to hopefully make it all work first time. So let's get it moving. All right. Denley, are you able to see that slideshow?
Yes, we can.
Lovely. Sorry, I've just got the technical side giving me a bit of a hand on this side. All right, I've called the presentation Lithium 101. I have taken an interest in lithium and lithium battery fires over the last most probably 5 years. There is so much development and change taking place, so much misunderstanding of what is happening. I don't want to say misrepresentation, but that might actually be a better word. So the way forward is for all of us just to have a far better understanding of what lithium is. And the question that a lot of people ask are lithium battery fires a real concern? Well, if we look around us, we will notice that lithium batteries are pretty much in every single appliance that is surrounding us today. Going from the scooters, cell phones, walkie-talkies, appliances that we have. So the answer is yes. Lithium battery. Yes.
Could you put it into presenter mode? It doesn't seem to be on the full screen.
Is it in presenter mode at the moment?
Not
All
at
right,
the moment.
let me get it out of there. Is it now?
It's not full screen at the moment. It's just a
Okay, we're sort of going back to the old SABS television. Please be patient. We have a problem. I'll stop sharing and start again.
okay. I'll
See
let
if
you know when it's full
that
screen.
makes a difference.
Yeah, I think it's because have you got two screens?
I do have two screens.
Yeah, so you
yes.
need to take out the one screen and just concentrate on your laptop to share because we're getting the two screen sort of vision. Yeah.
Okay. Are we still in presenter mode?
Not yet. We can only see you.
We're very lucky actually that this is almost like a trial run. So the first presentation is next week. The second presentation is this week. It's not often that the second presentation becomes before the first presentation. What mode are we in now?
Okay, we can see two screens. One is your presentation and one is you. I think you need to share on your one, not on the second screen.
Okay, I have the technical side working to try and get that right.
I think it would be better if you work off just the one machine and not two. Does that make sense?
Okay, it does. All right, they're just going to unplug the second, and let's just work off the one. Okay.
Yeah.
And that now?
No, it's still doing the same thing.
Sound. Can you hear me now?
I can hear you, but your presentation's not up yet.
Okay, now?
No. Okay. All right, now it's right, and now make it into presenter mode. There we go.
Ah, lovely. All right. All right, so sorry about that. It's always great to have a presentation that doesn't start exactly as you would like it to. Just going back, so I'm going to jump back onto a slide where I spoke about the presentation being a Lithium 101. Originally, I wanted to term it Lithium presentation for dummies. I didn't believe that would go down very well. 101 sounds a lot better, but it also just covers right from the very start of lithium. And the question that was posed, are lithium battery fires a real concern? And the answer is yes, very, very, very much so. Within the world that we live in today, we are surrounded with lithium batteries. The question that a lot of people say, will something else not succeed lithium batteries? And the answer is yes, more than likely. In time, something will. But there are massive amounts of money invested in the development of lithium batteries and in the mining of lithium as well. So it's most probably a little bit like petrol and electric vehicles. The people making the lithium batteries will be a little bit reluctant to give up their investment. So I do believe that lithium batteries will be around with us for a long time. Now, in today's presentation, I prefer to take us on a journey, and that journey we will start right at the beginning with lithium and lithium batteries, where we will look at the makeup of a lithium-ion battery. We will have a look at the chemistry of lithium, how it's sourced, and its chemical properties. We'll get to understand the phenomenon of thermal runaway. These are words that people like to throw out there, but very seldom actually understand what they mean. And then we'll get into the actual fire side of it, where we'll get to understand how they're extinguished. We will look at 3 categories of lithium fires. You won't find the categories in any research that you do. I've subdivided lithium fires into 3 categories, and when I get there, you'll understand exactly why I've subdivided it that way. But underneath each of those categories, we will look at test requirements and methods of testing. We will look at portable fire extinguishers and whether they pertain to any or all of the categories. And we will look at containment of possible fires. Then the presentation will end up by looking at what the world are considering 2 critical areas at the moment: the risks of lithium-ion battery fires, and then action plans which should be taken. So with that in mind, let's have a look, starting off with the makeup of an actual lithium battery. Now, in this slide, I show you on the left-hand side the very old lead-acid battery. That battery had caps. One opened it up, one put distilled water into there, and put it in one's car or wherever it was supposed to go. That was replaced by a gel battery. Gel battery, self-contained, no distilled water into it, and that is now morphed into what we now have as a lithium battery. And I think the one thing to note here, because we're going to come back to this part a little bit later on, is that all of them are predominantly housed in a plastic housing. But the first 2, the lead acid and the gel, are very, very different to the lithium battery. So let's have a look at the makeup of an actual lithium battery. The battery is made up of many, many small cells. If one prefers to term it small batteries, you can term it small batteries. Now, each of those batteries is made up of a cathode, positive side, an anode, negative side. Then there's a separator in between, same as any little battery is actually made up. The separator is to prevent the anode and the cathode from touching, because if they touch, there's a short circuit and no current will flow at all. And then the main part around that, all of that is housed in electrolytes. Now, we're going to come back to that electrolyte issue later, because that forms a large part of the fire makeup that we're going to be talking about. On the chemistry side of lithium, and this side I find very, very interesting. Let's first of all look at how lithium is obtained. Now, there are 3 methods of mining or extracting lithium. And this is most probably just a lot of useless information coming to you, but I think you'll find it very interesting information. The first method of mining lithium is known as brine-based extraction. The second is hard rock mining, and the third is direct lithium extraction, known as DLE. So let's go back to the first one, brine-based extraction. So brine is a mixture of lithium and other minerals. It's deep down underground. That brine is drawn to the surface and it is placed out. It's a liquid, very, very much like a salt pan, placed out on the surface, and the water is allowed to evaporate from the brine. The interesting part here now is that on brine extraction, up to 2.2 million liters of water are used to produce 1 ton of lithium. Remember, we're talking about a green product. 2.2 million liters of water are used to produce 1 ton of lithium. That water is not recoverable because, like in a salt pan, it evaporates. The concern that areas have, and this is usually done in very arid areas. For example, Chile is a very popular, if we can call it, destination for extracting the brine from underground water, bringing it to the surface. It's great. It's bringing a lot of income to Chile. The problem is, though, that it is affecting the farmers and the amount of water that the farmers have, and they are finding that they don't have enough water for crops. The second method that we have is hard rock mining. That's exactly as the term says. Rock with lithium in it is extracted, it is crushed, it is then mixed with water to try and separate out. And in the hard rock mining, most probably 400 odd liters of water are required to produce 1 kilogram of lithium. The possible advantage of that is that that water is recyclable. Then the last method was direct lithium extraction. Direct lithium extraction is a method used where chemicals and water are used to extract the lithium. The problem here again is that the water requirement is still between 400 and 2,000 liters of water required to produce about 1 kilogram of lithium, although that water again is recyclable. So that's just some useless information on how lithium is obtained, how it's extracted. The main lithium mines currently are in South America, in the deserts there, but also being found in North Africa and in Russia. Right, if we can move on. Now we're going to have a look at the pure chemistry of lithium. So, what do we know about lithium? Lithium is a soft, silvery white metal. It heads up group 1 of the alkali metals group, and on the periodic table, it has an atomic number of 3. Now, most probably for most people, what I've just said now doesn't really mean very much. So let's just go back and dissect that. An alkali metal is a chemical that can dissolve in water. So already one goes back to that underground extraction and say, well, how do you extract this heavy mineral, this heavy metal out of the underground? Well, it's dissolved in the water, and that's the brine part of the extraction that takes place. So it's able to dissolve in water. An alkali metal is also able to combine with acids to form salts, and they're also able to be added to acids to make acids less acidic. The 3 that you can see in the left-hand corner of that little square, that's the atomic number. Now, the atomic number, what it tells you is how many electrons there are moving around the lithium, or how many electrons there are in a lithium atom. The electrons, there will be 3 electrons, and then in the nucleus, there will be 3 protons. So if you look at the charge of that unit, that atom at the moment, it has a negative charge. It has a neutral charge. the positive of the protons and the negative of the electrons counter each other out, and that little atom sits quite happily on its own. The concern with lithium is that lithium only has one electron in its outer shell. So it's got these 3 electrons, 2 are in an inner shell, and 1 is on the outer shell. And that electron in the outer shell tends to want to head off and party as much as it can. It wants to jump out of this atom that it is, and it is able to do that fairly easily because there's not a lot of force holding it back. If an electron does move out of that atom, that is now what is known as an ion. So an ion is an atom, or it can be a molecule as well, that has either a negative or a positive charge. So if I take one of those electrons out, that electron heads off and it goes and joins somebody else, that lithium atom would be an ion. It would have 3 protons in the middle, which are positively charged, and it would only have 2 electrons on the outside. So that atom would become a positively charged atom. That is what is known as an ion. So we have 2 parts. Lithium, as it is the metal, pure metal, and a lithium ion, which has an atom missing. We will come to that later when we start delving a little bit more into the batteries and how the fires are concerned. Now, the one thing that we do know about lithium, it reacts vigorously with water, so storing it is a major problem. It can't be kept under oil. Other alkali metals that you might all well know about, being lithium, sodium, potassium, all products you've heard of. Those are all alkali metals. Those can be held and contained under oil or whatever. But lithium is so light that it pops to the top of oil, and you certainly can't put it into water. It reacts vigorously, and we're going to have a look at that reaction now. So that's sort of touching the surface of the chemistry of lithium. Let's have a deeper look into lithium and certain of its properties. So we know that it's an alkali metal, and we all understand an alkali metal. We understand that it's unstable. It only has 3 electrons, 1 in the outer shell, and that one likes to head off and go and join another party if it can. It's extremely light, and it will float on water. In a battery scenario, venting lithium-ion cells usually produce carbon dioxide, but it's produced in a very small form. It's not actually a problem. The problem with the lithium and pure lithium is it reacts with water, and it forms an hydroxide and hydrogen gas. But one of the hydroxides that it does form, which is very concerning, is hydrogen fluoride. And hydrogen fluoride is deadly to man. Hydrogen itself, as we know, is highly explosive. So we put lithium, pure lithium, into water. Hydrogen will come off as a byproduct, and there is a very good chance of an explosion. The lithium fire, and this is where a lot of people don't understand it, once a lithium-ion battery is on fire, it begins generating its own oxygen. Now, that means that you can't put it underwater or smother it or try and prevent oxygen from coming into it, because it doesn't matter. It's generating its own oxygen. When heated, and this is one of the new findings that have come through fairly recently, VOC gases, or what are known as volatile organic compounds, are formed. And these are formed from the vaporized electrolytes. And remember when we were looking at the original battery, and we looked at the cathode, the anode, the separator, and those are all housed in electrolytes. Well, these electrolytes are what causes the main problems with a lithium-ion battery fire. But the vaporized electrolytes, as I have already pointed out, consist of hydrogen fluoride. And this starts being generated from anywhere around 170 to 500 degrees Celsius. Now, burning lithium itself creates a metal fire of very, very high temperatures. And those temperatures can go from anything from 1,500 to 2,000 degrees Celsius, and they can get to that temperature very, very quickly. Just to help give everybody a little bit of understanding of temperatures, an orange flame, a normal candle orange flame, is around 1,100 degrees to 1,200 degrees C. The little whiter flame that one sees, they're getting hotter. So that's around about 1,300 degrees to 1,500 degrees. And then the brighter the white gets, the higher the temperature. Well, our lithium can get very quickly up to 2,000 degrees C. Lithium-ion battery fires become very, very serious because of a feedback loop that occurs within the batteries. And what that feedback loop does is that one battery starts getting hot, it then goes further and it starts overheating. From the overheating, it starts setting off the batteries, those little cells next to it. They start heating up as well. The first one possibly catches a light and is in fire. Then the second, the third, and that loop, which just continues throughout the battery with all those little cells that we saw in that original picture, that feedback loop is what's known as thermal runaway. Now, most probably best for us just to have a look at thermal runaway, and this diagram is going to give us a far better picture. So it starts on the left-hand side and moving across to the right. And on the left-hand side, we have three of those tiny little cells that could be in a battery. One of them starts heating up, and it could be because it's been abused. We will have a look just now at what could cause it to heat up. And then around about 170 degrees, the first sort of vapor comes off. Now that vapor we will talk about a little bit later as well, because it's also very, very important to know, because that's one method of detecting whether a lithium fire is about to take place. Okay, so about 170 degrees, that little cell is getting very hot. It's heating up the cells next to it. It's causing that feedback loop. And at a point, the first cell catches fire. And before you know it, the cells around it are catching fire. That process going from left to right is what's known as thermal runaway. Now, a little bit of information about the thermal runaway. Once one of those cells has caught a light, it is not possible to extinguish the fire that cell is generating. We're going to have a look at that later, but just bear that in mind, because there are organizations that say that they can extinguish that cell that's actually catching on fire. Once it's on fire, you cannot extinguish that cell. That is the thermal runaway side of it. All right, let's have a look quickly at then what can cause these cells to heat up. So with a lithium-ion fire, generally the cells will heat up, or the possibility of them heating up will take place when a battery is on charge. It sort of makes reasonable sense. Or it could be if one of those little cells has been punctured and the electrolytes are leaking out, and they come into contact with an ignition source. And we already know that the hazard with our lithium-ion batteries is more about that flammable electrolyte than it is with anything else. The lithium itself is the actuator. It causes that fire. The electrolytes are what then cause the real heat and the fast burning. So a battery overheating, what can cause that? Well, spontaneous internal or external electrical fault, like a short circuit, for example. If the battery is punctured, within electrical vehicles, EV vehicles, this is one of the big concerns of an EV vehicle being involved in an accident, and the battery, which is on the undercarriage of the electric vehicle, somehow getting damaged, punctured. Very good chance of a fire. Overcharging of the battery itself. External heating or a fire. That's external heating is, we'll come to testing just now of batteries, and you'll see the one way that test houses get the battery to go into fire is to heat it, which causes obviously it to burn. Mechanical abuse is another method, or it could simply just be a manufacturer's defect. But as you can see, there are quite a number of ways that a lithium-ion battery could overheat and therefore could go into thermal runaway. So, okay, we've had a look at how lithium is mined, and I'm sure there's a reasonable amount of concern around that. We've had a look at the chemistry, the molecular structure of a lithium atom, and the properties of lithium. We've looked at that. We've also had a good look at thermal runaway, and then the possible causes of thermal runaway, overheating, overcharging a battery. So let's move on. Let's look at now, we've got this battery with us, and we might need to extinguish a fire. Now, as soon as we talk extinguishing of any fire, the first thing that comes to mind is the fire triangle. And on the fire triangle, there are 4 methods of preventing a fire or extinguishing a fire. The first one is you can, and this is no particular order, you can remove the fuel. The other is you can remove the oxygen. For example, you can put a blanket over it and take the oxygen away. You can remove the heat. You can use water to try and cool the product down that's burning. And the fourth method is you can destabilize the chemical reaction that's taking place. And while we're onto that chemical reaction, here's some useless information which I know most people don't know, but and I'm sure all of you do know this, but if you don't, let me just repeat it, that the extinguishment of a fire using a dry chemical powder extinguisher, as I say, I'm sure you knew this, but it does not work by smothering the fire. That powder works on breaking up the chemical reaction of a fire. And I know that most people believe that the dry powder that you put on from your fire extinguisher onto a fire covers it like a blanket. That's partially what it does. Yeah, it can be a means, but its actual purpose is that powder has a means, and I won't go into it now, but if anybody would like to know later how that works, I will happily explain it. It breaks up the chain reaction that is taking place in a fire, and a fire is better known as combustion. So the chemical powders that we use that are inside a fire extinguisher, so that sort of maybe nobody takes any concern of, they actually have a very important job to do, and that job is they break down the chemical reaction. All right, let's look at the lithium battery itself. And before we look at how to extinguish it, there's certain things that we need to bear in mind. First of all, we need to bear in mind that that lithium battery is made up of lots of very tiny cells, or batteries, if you would prefer to call it that, and they're inside a casing. They're contained. They're not loose. Secondly, lithium produces its own oxygen. Thirdly, a lithium fire's reaction is very, very quick, and it's extremely hot. So if we have a look at that triangle, we start on the same direction that we started with when I first showed you the triangle on the fuel side. Very clearly, we can't remove the fuel. The oxygen, well, we can't remove the oxygen because it's generating its own oxygen. The chemical reaction, we are not able to change the chemical reaction. I have a personal belief that in time, that's most probably going to be the area that will be attacked and will be dealt with, is somebody will come through and have a method of changing that chemical reaction. That is only just a belief of my own. Then the last part of that triangle that we have, excuse me, is the heat. We can't stop the heat from the cell that's burning, but we could possibly cool the cells around it so that they don't burn. So currently, that's the only way we have of preventing a lithium-ion battery from going into total thermal runaway. The problem with these fires, because they are so quick, that the fire may only be discovered when it is far too late. And I know that all of you by now would have seen many videos, and I'm not showing videos on this presentation because I know that you would have all seen so many of them already, of lithium-ion batteries going into fire. They go into fire very, very quickly, and the fire doesn't last long. If you're looking at a small cell phone, for example, and we'll talk about this later, a cell phone, if it goes into fire, it'll burn for between 2.5 to 3 minutes, then it's burnt out. But the damage it might have caused up to that point could be absolutely, absolutely devastating. So now that we know that we need to deal with the heat side of a lithium-ion battery, let's go back, and this is something now that I've done. I have divided lithium-ion battery installations into 3 categories. And I think you'll understand by the time I've gone through the 3 categories why we've set it at 3 categories. So the 3 categories that I've got are small fires, medium size, and large. The small fires are fires that generate an energy of equal to or less than 600 watt hours. We will talk about that in more detail now. Then the medium-sized installation, these are installations where people will have cabinets and offices. They might have solar panels in their roof, generating or helping to provide the energy to recharge the batteries. These batteries are either stored in a cabinet or they're stored in a room. And then you end up with the large side of the battery installations, which are your energy storage systems, or ESS, as people prefer to call them. The same term, BESS, which is a battery energy storage system. They are in essence the same type of product. Okay, so knowing that we've got the 3 categories of installations, let's have a look. We'll start off with the small category. Small lithium-ion fires, less than 600 watt hours. Now, it's very easy to determine the watt hours of a battery because the watt hours is equal to volts times amp hours. And if one takes any smallish battery, probably the most common battery is the battery that goes into a fire panel. and there it will say 12 volts, 7 amp hours, for example. Very easy to then work out the watt hours of that battery. Now, with the small side of fires, there are a number of organizations conducting testing on these batteries to try and find the best means of ensuring that the fire doesn't spread. Organizations such as UL, LPBC, there are a number of universities conducting tests, and there's an organization called Kiwa. Kiwa is a Dutch test house. And the types of product, the types of mediums that they're using really varies. I was talking to somebody from Newcastle University. They've run tests using liquid nitrogen to try and cool the battery down. There are tests on normal water, just dumping water on, in other words, using water mist, D-class powders, using wet chemicals, which are often referred to as encapsulators. And I'm sure that you've heard the term AVD, which is aqueous vermiculite dispersion. By the way, and here's some more useless information. I know that everybody in the seminar will know what vermiculite is, because vermiculite is very, very well known in the fire industry. When one is walking in the Drakensberg or possibly through the Karoo, and you kick up the dirt, there's often that sort of little shiny, flaky piece that is around, and that is vermiculite. Now, vermiculite has been used for many, many years in passive fire protection, and it's used because of the properties that it displays. And its main properties are it's a very poor conductor of heat, and secondly, upon being heated, it expands, and that creates an additional protective layer. So, for example, if we took a cell on its own, a burning cell, and we could pack it with vermiculite, the chances are that the fire and the heat wouldn't be able to be transferred to the next small cells, and the battery that is burning would burn out, or the cell that's burning would burn out, and that would be the end of the fire. So what some organizations have done, they've taken that vermiculite, they've crushed it, they've turned it into a powder, they've mixed it with water and water additives so that it can go into a fire extinguisher. It can be dispensed. It most probably falls under the wet chemicals or encapsulator banner. So, testing of these small fire extinguishers. Now, currently, and we need to bear this in mind, that there are no international standards pertaining to lithium ion fires. There are organizations that have done approvals, and they are internal local approvals. The one that is most probably used the most today is the Kiwa test that is done. They've created their internal test. Remember, this is the Dutch standard. They've created their own standard called NTA 8133, and that's their method of testing small battery fires, batteries going up to 600 watt hours. So you can see now why I've limited small batteries up to 600 watt hours, because that's where the testing is limited to on fire extinguishers. Now, we already know that once thermal runaway occurs, it's very, very difficult to stop. The way that the tests are done, two tests that I'm aware of, the Kiwa test, Newcastle University are also doing tests. So the Kiwa test, they put about 5 cells next to each other. They set one alight, one on either end, not both ends. They set one of the end batteries on fire. They do that by heating it up. And then as soon as it starts burning, they will put the medium of the fire extinguisher that they are testing onto the remaining cells, plus the one that's burning. And the objective of that is to prevent thermal runaway, or to see if the medium that they're using prevents runaway. On the Kiwa test, there is no pre-burn. They allow, as soon as the first cell, the N cell, shows a flame, you are allowed to then put the extinguishing medium onto the remaining cells plus the burning cell. Newcastle University do it a little bit differently. They stack 6 to 8 odd batteries. They put the bottom battery into burning mode, and they then, once it is burning, wait for 1 minute pre-burn, and then they will discharge the medium, the contents from the fire extinguisher onto those cells. They stack something like between 6 and 8 cells, obviously depending, also just going up to 600 watt hours. And then they will wait on both instances. I think the waiting period is about 20 minutes to make sure that thermal runaway doesn't start again. In the real world, on the bigger batteries, thermal runaway has been known to start again after a day's period. But in these instances, now we're talking small fires only, it's a 20-minute waiting period. Okay, so we're talking about fire extinguishers extinguishing. It's very interesting to note that the NFPA do not promote the use of portable fire extinguishers on lithium fires. And the second point to note here is, if one is looking at a lithium ion fire extinguisher, it most probably would be best if the medium had been Kiwa tested, in other words, to NTA 8133. But maybe more importantly is to look at the actual discharge distance of the medium. I have seen a large number of videos where the person doing the testing has literally got to stand right over the battery, because the discharge distance of the medium coming out of the fire extinguisher is around about a meter, if not less. It's also noted that the person doing the testing is fully clothed in fire protection garb. Now, imagine a layman using a product that can only discharge a meter and trying to walk towards an extremely hot fire where those little cells that we saw in the original battery are exploding and firing in all directions. It could be a concern. Lithium ion extinguishers that are used in the market today. So they range between a 1 liter and a 9 liter unit. I am simply going to give the names. This is not a discussion of whether I believe they work or not. That's immaterial. But the mediums used are predominantly wet chemicals, water additives, wet vermiculite. I've put wet vermiculite on its own because it could be included as a wet chemical. But I know that people like to separate it. And then D-class powders as well. The wet chemicals that are on the market today, and I'm just going to name a number that one will possibly see in South Africa. Lithix, F500, Fireblock, Flame Block, FFX Lion, which is a fluorine-free product. On the extinguisher side as well, you'll notice that I have also mentioned D-class powders. Now, a lithium fire is not a traditional D-class fire. Although what I have discovered is that there are some D-class powders that have the ability to absorb heat from a fire. I'm unfortunately not aware of these, but research has showed me that there are definitely D-class powders that do have an ability of absorbing heat. And if one can take the heat out of the fire triangle side of it, then yes, there's a possibility that that would be a product to be used. Therefore, I've left it as one of the products that can be used. The word encapsulator most probably is bandied around as much as thermal runaway. Encapsulator is simply what it says. It encapsulates, it surrounds a product, and the encapsulators that we are referring to, the wet chemicals that are in the list above, are all referred to as encapsulators. Their job is to surround the cells, to cool them down, and therefore the aim is to prevent thermal runaway. One of the top encapsulators, by the way, is graphene, and this is also just another piece of useless information. Graphene is a byproduct of carbon. It's very expensive to harvest, to obtain, but it is highly effective. If graphene is surrounding a cell, the heat will not be able to disperse out of that cell, and possibly in time, graphene might be used. But the research that I've read is that graphene would most probably replace the lithium-ion battery, because graphene on its own can store huge amounts of energy, and you would be able to have a fairly small cell. A lot of work has to be done, though, on the graphene before it becomes a commercial product. Okay, the last part, and this is where throughout the world containment appears to becoming the buzzword. How do we contain the fire? What should we do? The containment of small lithium-ion battery fires. First of all, practical storage. We're most probably looking now at households. Somebody might have a solar panel. They've got an inverter. It goes into 2 batteries that they have. And the practical storage is, where do I put those batteries? Well, it's not advisable to have them in one's lounge, next to furniture, next to curtains, what have you. It's equally not as advisable to store them in one's garage. I think the containment side would be to have something built outside of the house, brick, solid, where the batteries can be stored. If anything happens there, that basically ends up as being the containment area. The batteries can burn out and there's going to be a horrible fire, but it's most probably not going to affect anything else. Fire blankets. A lot of talk around fire blankets. I'm going to come back to that now as well when we talk about medium fires, because there's been a lot of change and a lot of research done on fire blankets. Fire extinguishers. We've been through the fire extinguishers side of it already. And then there's the sound housekeeping, which pretty much goes with all fire scenarios, whether you're in a massive factory and whether you have lithium batteries or not. Sound housekeeping is always the number one go-to for trying to prevent fires from spreading. Okay, so the question that's often been asked to me is, what is the purpose of portable fire extinguishers in a lithium-ion battery fire situation? And as I've already pointed out, NFPA don't promote the use of portable fire extinguishers at all. Personally, I believe that they do have a purpose. The purpose, number one, being if you have the possibility and if the medium has the possibility of extinguishing and preventing thermal runaway, then I would rather know that I had that possibility than no possibility whatsoever, and I was going to allow thermal runaway to continue and the batteries to burn. But the other side of the portable fire extinguishers is the secondary side. So a fire is generated inside a battery, and it starts burning furniture or curtains, something like that. I would rather have a fire extinguisher with a wet chemical product that does spray a reasonable distance. So it's got the discharge distance is important, and that the secondary side is I can put out that curtain if it has caught a light. Those of you who've seen videos of a lithium-ion battery catching a light, is that once that casing gets hot and it bursts open, those little cells become massive projectiles, and burning projectiles are shot all over the show. Certainly something that a layman would not go anywhere near. Even firemen tend to keep their distance. But those cells now that are being ejected from this battery, which is now broken open, could be shot across the room, touch a curtain, set it alight, and that's a secondary fire. So that's why I believe that there is definitely a serious purpose for having a fire extinguisher available. All right, I think we've covered the small lithium-ion battery fires in fair detail. Most probably why I spent more time on the small battery than any other is because there are tests being done, and there is the possibility of a standard. We spoke about the Kiwa standard. From what I'm understanding, that won't be the ultimate standard. There will be derivatives of that will eventually morph into an international standard. But the Kiwa standard is the start, and I think it's going to be the founding father of a standard for small lithium-ion batteries, which go up to 600 watt-hours. All right, let's move on to a medium-sized lithium-ion battery. Now, this one is most probably more interesting than any others, because there are many offices, there are many buildings that have more than one small battery. They have a number, and they're either housed in a cabinet or in a room or what have you. So the example that I've given here is we have 5 12-volt, 100-amp-hour batteries. And if you work that out, you will end up with those 5 all add up to an energy of 6,000 watt-hours. So straight away, your fire extinguisher is out. Now, there are a lot of organizations that are saying, yeah, but you have to put a fire extinguisher next to that. I'm not telling you whether you do or don't, but I will leave it up to you to determine whether you believe a fire extinguisher would be a solution. Okay, the problem with the medium-sized installations is that there is little to no research being done on this. So on the medium-sized installations, we simply have to go to containment. And on the containment side, the original containment sides were fire blankets, throw it over. If it's an electric vehicle, throw it over. Gas detection, so try and detect the fire. What is that going to do? It's going to enable one to possibly remove the active battery and put it into a containment area where it can either burn itself out or stabilize itself. There are aerosol units in the market which claim to have an effect on the medium-sized battery fires, and then there are fireproof cabinets as well. Now, where there has been a massive change is on the fire blanket side. Up to 3-4 weeks ago, fire blankets were the thing to use, particularly on electric vehicles, and the philosophy behind this was that if an electric vehicle is on fire, one puts a fire blanket over it, one drags the vehicle away, or if you can, get it onto the back of a vehicle, take it to a containment area, park it, leave it there, and let it burn out. Well, as I say, in the last 3 to 4 weeks, an NFPA study has come through where they're saying no, under no circumstances put a fire blanket specifically over a electric vehicle that has that's caught on fire. And they're saying this because of the buildup of the VOC gases. Remember the volatile organic compounds that we spoke about much earlier on? Those build up underneath that fire blanket. They are trapped underneath there. And they cause a phenomenon known as deflagration. And deflagration is a form of combustion where flames propagate at subsonic speeds. It's deflagration is almost like a cousin of flashover. If you're not sure what flashover is, it's a normal building is burning. This heavy smoke rises. It's held on the ceiling. It gets to a point where it gets very, very hot, and it burns, but it burns as an explosion. Very, very dangerous. So the NFPA study is now saying, do not use fire blankets. It's actually too new. I have put it into this presentation, and I purposely left it in the presentation because it's a concern, and to be honest, I don't know what the replacement would be, apart from using the other 3 methods of containment. All right, let's move on to what is the real deal in large lithium-ion fires, and those are your energy storage systems. And this is where the real concern, the real research is being done. And here, NFPA are doing most probably more research that I'm aware of than anybody else. And their research goes into the energy storage systems fire spread. And they are looking at a number of areas. If I can break it down to 3, and it's not limited to 3, by the way, but 3 areas that we would most probably understand best. The first one is container separation. So their white paper, it's not yet a standard. So these are white papers are like suggestions. And those suggestions then need further research before they actually become standards. They look at container separation, and they say that a container must be at least 1 meter apart. And if you look at those pictures on the slide now, those are a lot of containers. Then the other thing that they look at is inside the container itself. They look at separation, and they have a 2-hour fire rating. Now, if I stand to be corrected, but their separation is they have about 8 batteries together. Then there has to be a gap and the next 8 batteries, and I might have the number of batteries incorrect. But there has to be, if one of those groupings of batteries go into fire, there's got to be a 2-hour separation between them and the next battery. 2-hour separation horizontally, and if somebody has put batteries on top of it, there's got to be a 2-hour separation vertically as well. And then they've also limited the size of the enclosures to not exceed 16.2 meters by 2.6 by 2.9. That's pretty much the size of a standard container. So they're saying you may not house these batteries in anything larger than a standard container. If there's further interest shown in this, my suggestion is have a look at UL 1973. You can also look at UL 9540, and you can also read through NFPA 855. These are all papers about separation. And certainly as an insurance company or as an underwriter, you might find these very interesting. Then also with the storage, contain the energy storage systems, one looks at detection, removal and containment and extinguishment. And in looking at those, if we look at the fire detection side of it, inside a container, there are temperature probes that one can use to put onto each battery. There are gas detectors detecting that very early fume that's coming off from the battery before the battery's actually gone into fire. There are thermal cameras, and there are aspirators that can also be used. Personally, I prefer the thermal camera, and the reason why I prefer that is that thermal cameras can be set to pick up a temperature that then gets relayed to a guardhouse or a control room where it can be viewed. But more than just being viewed, if somebody has to go to that container to try and remove that battery, which is now getting hot, they can see exactly where that battery is. The other methods, one would go into a container and possibly not know where that battery is. One still has to be pretty brave to get into the container, go to the battery, uncouple it, take it out and put it into a containment area. There are suppression systems. Siemens have a suppression system. It's nitrogen and an aspirating suppression system. Aspirator used to detect the gases, nitrogen used to suppress. To be honest, I'm not quite certain what their method of operandi is here, and what on the fire triangle they are attempting to remove. One can research that a little bit further. There are automatic sprinkler systems. The company that center that we represent in South Africa, Reliable Automatic Sprinklers, they have the only UL approved sprinkler head, which they've used to extinguish the batteries in your large energy storage batteries. And then there are also water mist systems. On the large energy battery sides, when I spoke to a professor from Newcastle University, he said that the wet chemicals, the encapsulators, and the water mist systems appeared to be the most effective. And then your last part of containment is removal. On the manufacturing of batteries, for example, they use thermal cameras. If a battery coming down the line has a fault and it is getting hot, the camera will pick it up. That battery is simply removed and put into a containment area, and if it's going to burn, it burns out there. There's no other extinguishment that's used. It's simply a containment area. Your energy farms, for example, will all have containment areas to remove and put install a battery. Excuse me. I just need to get something to drink. All right, we're coming right to the end of it now, the presentation. So two other things I would like to just quickly look at. One of the risks, and the other one is an action plan, which I think is very important. So the risks associated with lithium-ion battery fires, there was always only a primary risk. And the primary risk was fire, and something was going to burn down. There's now prescribed a secondary risk, which people are finding maybe even more serious than the primary risk. And the secondary risk are the VOC gases, the volatile organic compound gases that are produced. Because it's shown that a 1 kilowatt battery can produce anything from 500 to 1,000 liters of gas. And in that gas is your hydrogen fluoride, which we do not want to be associated with. With that in mind, we would need to look very carefully at creating an action plan. And the recommended action plan is to create an emergency response, not just for the staff, but for firefighters as well. And by the way, this doesn't just apply to your energy storage systems. This would apply across the board to small fires, medium fires, or large fires. So what should that action plan include? It should include fire alarms. So the fire alarms would be associated with detection. The gases are detected, or whatever means of detection one has used, that will allow people to move away from an active area. It must include a means of escape. It's no point having a battery housing in the front of an office where the batteries have now gone into fire and people can't get out past the front of an office. There should always be access for firefighters to get to wherever the situation could be. There needs to be provision of water, in other words, fire hydrants. Very, very important is your smoke extraction or your venting. So even in an office scenario, one needs to now make sure, and that's something that wasn't taken into consideration before. One said, I have my batteries, I've actually have a room, and it's a concreted room. In fact, it's got a concrete ceiling even, and I'm pretty safe. Once the batteries are burnt out, I will go into the room. That is definitely a no-no. There needs to be extraction, getting those VOC gases out of there as fast as possible. And there should be breathing apparatus available. So should somebody be suffering any sort of acuteness, one needs to be able to get them out of that scenario. In summary, lithium-ion batteries are made up of very smaller batteries, or actually cells, as they should be termed, and they're housed in a plastic or a metal casing. So one's not always able to get to them. Lithium is highly unstable. We've seen that from the chemical structure that it is. Thermal runaway is very difficult to stop. One needs to bear in mind that the active cell, the cell that's burning, you cannot extinguish that. But there is the possibility of cooling the cells around it down to a point that they don't go into thermal runaway. Lithium-ion fires burn at a very high temperature. The fire triangle shows us that the cooling of the battery currently is the method that one needs to extinguish these fires. One needs to bear in mind that the extinguishment and containment of the three categories, and that's the reason why I broke up the three to show three categories. The extinguishment and containment of small, medium, and large or energy storage systems is very, very different. And there is no one solution that fits all. We now need to also understand the risks associated with lithium-ion fires, particularly the VOC gases and how dangerous they are. And because of that understanding, we should always have a sound action plan. to go forward. Ladies and gents, I hope I haven't taken too much of your time. We've certainly gone through a major journey on lithium, and I hope everybody has a very strong understanding now of what can work and what can work and what doesn't work. And if anybody would like to ask any further questions you don't want to ask through the medium that we are now, you're welcome to email me. My email address is put up there. So I think without any further ado, I think it's now time for me to sign off, answer any questions. Beverly, I'm going to stop the sharing now, and hopefully we come back to the normal slide and we don't have any problems going forward.
Thanks, Duncan. I do have a few questions for you. How does lithium-ion batteries differ from the new sodium-ion batteries?
Okay, the main difference is if you look at the chemical composition and we go back to the periodic table, the lithium ion, the atomic number is 3. Sodium, sorry, offhand, I can't remember the atomic number, but it is higher. So in other words, the atoms themselves become more stable. There is, funny enough, and from what I had heard, Elon Musk was looking at a product called gallium nitride. Now, gallium nitride, if I remember rightly, has an atomic, or gallium has an atomic number of about 20. All it means is that the more electrons and neutrons that you've got, the more difficult it is to break one of them away. And that's the side with sodium as well. Remember, sodium is also an alkali metal.
Thank you. Should the power source from the inverter to the batteries be disconnected for extinguishing to be more effective?
Absolutely. If you can get to it, my suggestion is have a look at going onto YouTube. Have a look at a lithium battery that's on fire. And when one sees the sparks, and they're not necessarily sparks, they're those small cells literally shooting out, it's a scary phenomenon. And usually an inverter is pretty close to the battery. If you can get there, yes. And certainly the first thing you want to do is try and disconnect the battery. I'm not sure whether one would be able to, though.
Okay, Adele Abrams says, I have a client who has 6 lithium batteries that were damaged. His repairer reported that the cause is power surge. Insurers appointed a loss adjuster who appointed another electrician to provide a report, and our client's claim was rejected, saying that the batteries were faulty and it's not a warranty claim. They advised that the batteries could not have been damaged by power surge because there was no damage to the inverter. How would you determine which report is correct?
Okay. If there was a surge protector, and the power surge didn't get to the battery, if one remembers right at the very beginning, we spoke about what could cause batteries to heat up. Things like power surges, changes in power, can certainly cause a problem. And with the lithium being as we can say vulnerable as it is, yes, it could very much be a factor. I would find it difficult to understand why somebody says it's not a factor, put it that way.
Okay, next one, Melinda wants to know, is it a bad idea to have batteries, lithium batteries inside the house?
A very bad idea, yes.
Okay, can you use sand to lessen the impact of fire?
Sorry, Beverly, I missed that one.
Can you use sand to lessen the impact of fire?
No. Remember, the batteries are generating their own oxygen. So you can take that battery and you can, one is, if you go onto YouTube, you can see entire cars that have gone into fire. They've driven them into a swimming pool. There's quite an interesting YouTube video on that. And the battery carries on burning. No, because you can't smother a lithium ion fire. You can't put sand on it. You can't put a blanket over it, anything like that. So no, the sand won't work.
Okay, from Naveen, what are the main differences between lithium iron phosphate, nickel, manganese, cobalt, and nickel, cobalt, aluminium from a fire and explosion point of view? In other words, batteries with different chemical compositions. Based on your research, which are the most common types of imported into South Africa, and what types of products are they typically used in?
Okay, I think there are two parts to that question. The first question was, I have no idea. I would have to look up the difference between those. What is the most common lithium-ion battery imported into South Africa? I'm actually not aware. I would have to look that up as well.
Okay, thank you. How do you count that 2 hour separation between the lithium batteries? By walking for 2 hours in between them, or the spread of fire taking 2 hours in between?
One usually looks at a separator. So the separator might be a wall, a blanket, a curtain, or something that prevents the fire from getting across that gap.
Okay, I think that
It's quite interesting that you will talk about that, and that's an interesting question as well. They talk about that 2 hour fire rating, but they do not tell us how to go about it.
I've got
So
a
in other words, they're not
standalone.
prescribing to us.
Okay, a standalone never solar device with a lithium battery in. Can you use that inside a house?
There are quite a few devices now that are linked up with solar panels, where everything is all in one. So you have this metal container or metal cover with your inverter and the batteries and what have you inside that. I would have to leave it up to the person to decide whether they are happy to have that in their house. Unfortunately, there's very little one can do if those batteries do go on fire. There's very little, if nothing, one can do. A fire extinguisher wouldn't work because there's a hard covering, a casing around it. I see some of those do claim to have an extinguishing medium inside the housing. I'm not certain what that extinguishing medium is and exactly how it works. But yeah, for me personally, I would prefer to have that housing placed outside.
Thank you. Final question. I've heard that the best fire extinguisher to use on lithium-ion battery fire, most likely a small fire, is a gel extinguisher. Is this correct?
I'm not sure if that's correct at all. I think I know whose product one is talking about. Possibly it would be advisable to ensure that the product, the medium, in other words, the gel, has passed some sort of test. But from what I'm seeing and the research that I've done, the encapsulator type products, so the gel would fall under that category. The encapsulator type products are all relatively viable. I think all of their, and I might be shot for saying that, and remember, us as a company, we also have a lithium product which has been approved by Kiwa. I do think that they may be overrated and possibly could give a false sense of security. And here I'm just giving an absolute personal view, and I'm saying that about our very own product as well. I am very concerned with people having a false sense of security.
Okay, Duncan, I think that's all our questions. Denley, I hand over to you.
Great. Thank you so much, Duncan. It was so insightful. We've all learned so much. And thank you to Morris as well for arranging this. And just a reminder, everyone, we will be sending your CPD certificates, and it's 2 hours for the session. But thank you so much for all your support. Thanks so much again, Duncan. It was great.
It's been a pleasure. Thank you very much for having me. Thanks, everybody.
Thank you.
Cheers.
Thank you.